about connectivity properties of graphs. And on the last lecture, we defined connected components, and I formulated the general theorem which says that any graph can be always represented as a union of connected components. And the number of connected components is one characteristic of the connectivity properties, right? So we can write this down. So the number of connected components is one characteristic of connectivity of the graph. But that characteristic is rather crude, right? Within each connected component, if you pick any two vertices, you know that there will be at least one path connecting these two vertices, but you don't know how many different paths are there connecting two given vertices, how long these paths are. So we would like today to develop some method of answering this question. So given two vertices in a connected component, how many different paths of a given length are there between these two vertices? So that's our goal for today. And to do that, I will introduce the so-called adjacency matrix. Which is another way of representing a graph. We know already two ways. You can specify the set of vertices and a list of edges. It's one way to define a graph. Or you can just draw it and represent the graph by drawing. And here is a third way. And to encode a graph in its adjacency matrix, we first need to pick an order on the vertices. We order the vertices. So that means I'll label them by integers, vertex 1, vertex 2, vertex 3, and vertex n. Then define as a quantities a, I, j. So here I and j are two indices. Each runs from 1 to n. And this quantity a, labeled by two indices, equals to the number of edges between v sub I and v sub j. So the index I labels one vertex and the index j labels another vertex. And these numbers, we can put them into a table, which is called a matrix. So the numbers Aij can be put in a table called the adjacency matrix in such a way that I, which is equal to 1, 2, dot n, labels, the first index labels the row in the table, labels the row, and j, which runs over the same set of values, labels the column. so that it looks like this. We have the numbers A11, A12, A13, and so on in the first row. We have A21, A22, A23, and so on in the second row. So the last entry in the first row will be A1n and A2n in the second row, and so on with the last row. The nth row will look like this: an1, an2, dot, 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 and a and n will appear in the bottom right corner. So you can arrange all these numbers like that, and it's customary to surround it by brackets, which can be square brackets in some books, but I'll use round brackets. So this whole thing is a matrix. It's a square matrix because it has the same number of columns as the number of rows. Right? And more succinctly, one also sometimes writes for the whole matrix Aij in the brackets, right? Which means all possible Aij's standing in that table. Let me do a concrete example. Find the adjacency matrix for the following graph. So I'll draw the graph here. It has three vertices, and we'll label them as V1, V2, V3, which already gives us some ordering. If the vertices are labeled, say, by letters, then you can use alphabetic ordering. Right, so it would be natural. Right, so what are the edges? They're like this. Okay. So the adjacency matrix for this graph, let's call it capital A, it will be a 3 by 3 matrix because there are three vertices. And I can label the columns with the vertices and the rows as well. They're labeled by the vertices. So you can just write 1, 2, 3, or V1, V2, V3 to see that it corresponds to the vertex. And now we can fill in the table row by row. So in the first position, which corresponds to the row labeled by V1 and the column labeled by V1, we should put in the number of edges between V1 and V1. There is one loop, so I put 1 here. Between V1 and V2, there is a single edge, so I put 1 here. And between V1 and V3, there are 2 edges, right, drawn. So I put the 2 there. In the second row, between V2 and V1, we'll already considered that, so it should be the same number, right? And this table, in fact, is symmetric. If you swap the 2 indices I and j, which means swapping the row with the column, the entry will be the same. Because here we're not dealing yet with directed graphs, so the number of edges between a pair of vertices, right, doesn't depend on how you order these 2 vertices. So it's the same one as there. Between V2 and V2, so there are no loops on V2, so I put a 0. V2 and V3, there is 1 edge there, and I can put the same entry for V3 for the third row and the second column. Right, it's the same one. So what else is missing? V3 and V1, it's the 2, which we had before, it's the same 2. And finally, V3, V3, there's a single loop there, so that puts a 1. So the symmetry of the matrix, you can also imagine it as a reflection with respect to this main diagonal. Right? If you reflect about that diagonal, the entries should be the same. So this 2 gets reflected to that 2, 1 to that 1, and this 1 to that 1. Okay. So let's write this down. This is general property. So a note worth making. The first note is that the adjacency matrix is always symmetric. Which means that Aij is equal to Abi. If you swap the row to the position in the row to the position in the column, and it's the same entry. And also, if we had a simple graph with no loops and no multiple edges, so that would mean that on the diagonal we would get all zeros, right? Because what stands on the diagonal are the numbers of different loops. So for a simple graph, we have zeros on the diagonal, and for the off-diagonal entries, they're either 0 or 1. They cannot be 2, 3, or more, because for simple graphs there are no multiple edges. And 0 or 1 of diagonal, away from the diagonal, okay, for the off-diagonal entries. Any questions so far? Okay, clear. Now, next thing, to apply this to counting of paths, I need to use matrix multiplication. So I need to ask how many people here either do not know how to multiply matrices, square matrices, or just not confident enough in that. Could you please raise your hands? Okay, fine. So I'm going to explain this again. Matrix multiplication. So we will be only multiplying square matrices of the same size. So let A with entries Aij be an n by n matrix, and let B with the entries Bij be another n by n matrix. We define the product A times B, so you can either put a dot here or a little cross, that doesn't matter, just one matrix next to each other. A times B equals C as an n by n matrix C calculated by the following rule. So the result of the product is a matrix of the same dimension, n by n square matrix, and a single entry with the indices Ij, right, which is the same as A times Bij, is equal to the following sum of the product of entries of the matrix A and B. So it's Ai1 times B1j, it's product here, plus AI2 times B2J. I'm continuing plus AI3 B3J plus dot 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 until you arrive to AIN times B and J. Okay, and this can be illustrated on the following picture. So if you write both matrices and single out the ith row, which will have entries AI1, AI2, AI3, dot, 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 AIN. Okay, so I'm singling out a single row with a label I. And then I write next to it the matrix, the second matrix B with entries B11, B12, and so on. And I single out the jth column in it. So that column will contain the entries B1J, B2J, B3J, and so on, B and J. And I'm not writing out the other elements, but they're there. So what's written in that formula for Cij above is the following procedure where I take the first element in this row, in the ith row, the first matrix, multiply by the first element in the jth column in the second matrix, plus AI2, the second element in the row, times the second element in the column, plus the third element in the row times the third element in the column, and so on, until I exhaust all elements. And there are n of them in the row and n of them in the column. Okay? And that will give me just a single entry, Cij, which is sitting in the ith row and in the jth column. So you see that the process is rather laborious, because to calculate one entry in the product matrix, I have to do n multiplications and n minus 1 additions. So let me do an explicit example of calculating a product. So I'll do a product of 2 by 2 matrices, just to illustrate this concretely. So let A be the following 2 by 2 matrix with entries 1, minus 1, 2, 3, and B also 2 by 2 matrix with elements 6, 3, minus 2, 11. So if we want to multiply A times B, I write the two matrices next to each other. And I start doing my procedure. So I will be filling it in row by row and column by column. So first I take the first row and the first column in the second matrix, right? So first row in the first matrix, first column in the second matrix. And I get 1 times 6 plus minus 1 times minus 2. I'll leave the arithmetics for later. I'll put the whole thing in the brackets. And this is the answer for the first entry in the first row of the product matrix. Well, next I stay with the first row in the first matrix, and I take the second column, 311, in the second matrix. And I do the same procedure, 1 times 3 plus minus 1 times 11. I put this in the brackets to do the arithmetics later. That's my second entry. Then I go to the second row in the first matrix, and that gives me 2 times 6 plus 3 times minus 2. the same rule. Finally, second row, second column. 2 times 3 plus 3 times 11. Okay. Any questions so far? Right. And once you do the arithmetics for all of those entries, you get the following answer. So you get 8 minus 8, 6, and 39. Okay, so that's the product of these two matrices, A times B. Yes, please.
If A is, since you measuring these 3 by 3, what would you do?
I cannot multiply them at all. Not to mind. Right. Any other questions? Right. If you do B times A, so I'll do it quicker. I'll just write out the answer, and you can, apply the same rules and calculate for yourself as a method of practicing. And you can check that the answer is this matrix, 12, 3, 20, 35, which turns out to be different from the previous product, right? And what's the difference? The matrices A and B are the same, but the order of multiplication is different. So this means that in general, matrix multiplication is not commutative. If you swap the order of the two matrices, you can get a different answer. It's different from multiplying numbers. When you multiply two numbers, the order doesn't matter, and we say that multiplication of numbers is commutative. Here, matrix multiplication is not commutative. That means that in general, A times B is not equal to B times A. However, it is associative. It is associative. For example, if you have to multiply 3 different matrices, you can either first multiply A times B, and then the resulting matrix multiplied by matrix C on the right. And it turns out that's the same if you do first multiplication of B times C, and then multiply by A on the left. So I kept the order exactly the same, A, B, C, because I know I should be careful with the order, but the brackets, which signify the order in which I perform these two multiplications, can be moved around. Right? So that's good. Also, when we talk about multiplication, we know that when we talk about numbers, that there's a special number which is equal to 1. If you multiply by it, it doesn't change anything. There is also a special matrix called the identity matrix. And I'll be denoting it by this fancy style 1, and then labeling n times n, the dimensions of this identity matrix. And it looks like this. It's an n by n square matrix, which has 1s on the diagonal for all diagonal entries, and 0s for all of the off-diagonal entries. And it has the same properties as number 1. So again, the dimensions of the matrices, when I multiply them, should be the same. So if I take an n by n matrix A and multiply it on the left by this identity matrix, then nothing changes. I get A. You can do the same on the right. A times 1 and n by n. It also doesn't change anything. It gives me A. So it behaves just like multiplying by 1. Any questions about matrix multiplication? Okay, hopefully you've got the idea. To do it, so what's the use of it, of the matrix multiplication and the adjacency matrix? It's given by the following theorem, which says that the number of different paths between the vertices v sub I and v sub j of length n is given by a times a times a times a n times, right? So you do matrix multiplication of n copies, oh, not n times, n copies of A, and after that you get a matrix of the same dimensions, and you should read off the entry ij. Okay. So sometimes this, I will be writing this more succinctly. Instead of writing a times a times a with n copies, I'll write just a to the power n. All right. With multiplication, you also can define powers, integer powers, right? And then if you read off the single entry and that product of matrices, then it will give you precisely the number of different paths between the vertices labeled by I and j. I'm going first to do a concrete example in which I'll use this theorem to calculate numbers of paths, and then I will discuss, why it works. Might look mysterious, why matrix multiplication has anything to do with counting different paths. So I'll try to demystify that later. But first, the example. For the graph below, which I will draw, find the number of paths of length 2 from A to B. So now the vertices will be labeled by letters A, B, C, and from B to B. Also find the number of paths of length 4 from A to C. Well, so of course we're counting all different paths. Just for brevity, I'm not writing count all different paths, so it should be clear from the context. That's what we're doing, find all the number of different paths. And also when I say from A to B, it's the same as saying from B to A or as saying between A and B. So at the moment we're doing undirected graphs, so the order doesn't matter anywhere. Okay, so that's just to make this really clear. And the graph is drawn here. So I have the vertices of B, A, vertex C here. Looks like this. Okay, so what we're going to do. So first step, we'll find the adjacency matrix. And we will use the alphabetic order using If you choose any other order, it doesn't matter. If you stay consistent with remembering, which vertices correspond to which rows and columns, then your final answer for the numbers of paths will be the same. It's just a convention. Right? It has to be consistently used throughout the calculation. So for brevity, for simplicity, I'll just choose the alphabetical order. I'll call this adjacency matrix again by capital A. So there are 3 vertices, therefore it's a 3 by 3 matrix. And the columns will be labeled by A, B, C, 3 vertices, and the rows as well, A, B, C. So on A I have a single loop, so I put 1 here. Between A and B I have 3 different edges. So I put 3 here and in the symmetric position as well. On B I have no loops, so I put 0 here. Between A and C there's a single edge, so 1 here and 1 there respectively. Between B and C there's also a single edge, 1 here and 1 there. And on C there are no loops, so I put a 0 for that entry. So this is the adjacency matrix for this graph. And first we will calculate the numbers of paths of length 2. So length 2 means I have to multiply 2 copies of the adjacency matrix. Okay. So I take A times A, and to calculate that, I will write them 2 copies next to each other. So 1, 3, 1, 3, 0, 1, to be a bit larger, and 1, 1, 0. And another one, another copy. Then I go through my prescription, right? Taking the first row, 1, 3, 1, and the first column, so 1 times 1 plus 3 times 3 plus 1 times 1. So here it will be 1 plus 9 plus 1. That's 11, right? And continuing with the same rule, I get the following entries: 4, 4, 4, 10, 3, 4, 3, 2. You can save your work a little bit here, because it turns out if you multiply 2 symmetric matrices, the outcome is also symmetric, which means that it suffices to calculate the entries on the diagonal and above the diagonal, and then you can reflect it. Right, so you can kind of save yourself a little bit of time. So just put this down as a remark. A product of 2 symmetric matrices is also a symmetric matrix. Well, 2 identical symmetric matrices is also a symmetric matrix, right? So this can be used to save some save you some calculations. All right, having done that, now I can read off the numbers of paths. So paths of length 2 from A to B, that means I take the first row, which corresponds to A, and the second column, which corresponds to B, and look at that entry, which is 4. So that's the answer. So there are 4 different paths of length 2 from A to B. So just read off the answer. Here, this is a very small graph. I'm just doing it as an example. We can actually check ourselves. So it's not so hard to find all paths of length 2 from A to B. So for example, you have to use up to edges. So you can use first you can use the loop and go from A to A. That is one edge. And then you can pick one of the three edges between A and B to arrive to B. So that gives you three different paths. They're different because they pass through different edges. So indeed, check. There are three different paths of the form AB, right? I mean, if we want to write all three of them precisely, we should also introduce some labels for the edges, and then we can just list the two edges. But here, just for the sake of checking my result and illustrating that it is indeed correct, I'll just write it like AAB. So you go from A to A and then from A to B. So there are three different paths like that, but also you can go through the vertex C, A, C, B. And one more path, A, C, B. And indeed, altogether there are four of them, as we can read off. And also we're asked the number of paths of length 2 from B to B. So from B to B, I should pick the diagonal entry, which is in the second row and in the second column. And I see that the entry which sits there is 10. So there are 10 paths of length 2 from B to B. Again, if desired, you can find this path. All right, so you can quickly find 9 because you go from B to A, choosing one of the three edges, and then you can independently choose any one of these three edges to come back. So it gives you 3 times 3, so 9 paths of this form BAB. So that's 9. Or you can go to C and then come back, right? BCB, that's the 10th one. Okay. Let's now answer the final question. Find the number of paths of length 4 from A to C. For that, I need to multiply 4 copies of the matrix A times A times A times A, and then again read off the corresponding entry, right, which corresponds to the 8th row, the row labeled by A, which is the first row, and the third column, which corresponds to the C, vertex C. And you may think that, okay, we have calculated already A times A, right? That's the whole matrix up there. We can use that because this is already calculated. And then you may think, okay, then I need to multiply it by a copy of A one more time and by another copy of A. So that will give you 2 matrix multiplications. But in fact, we can group it like this and write this as A squared times A squared, because the multiplication is associative. And A squared we have just calculated. So this has only one matrix multiplication left. It's a lot less work. So I'm a lazy person, I'm going to do that. So I'm taking 2 copies of the square, A times A. So I take that matrix, I calculate 11, 4, 4, 4, 10, 3, 4, 3, 2, times the same matrix. 11, 4, 4, 4, 10, 3, 4, 3, 2. And here, well, it's not worth calculating the whole matrix because we only asked about one specific entry. It did make sense to calculate the whole matrix before that for the square because now I'm using it, right? But there are no further questions in this problem, so I'm going to calculate only one entry in the 4th power. So it's from A to C. It will be sitting in the 1st row and the 3rd column. Right, so I'm after this entry. And therefore, here I need the first row, and here I need the third column. And I can do my arithmetics separately now. So it's 11 times 4 plus 4 times 3 plus 4 times 2. So that's what I need to calculate to get that entry. So that's 44 plus 12 plus 8, or 44 plus 20, that's 64. So that is the entry which is sitting there, and that's the answer to my question. So it follows that there are 64 different paths of length 4, well, from A to C, from vertex A to vertex C. And you see that, in principle, these numbers, they grow rather rapidly. So these 64 paths, you can find them by direct inspection, but chances are you will miss some because you need some good organizing principle. But the main thing, the main advantage of this method is that you just have to multiply matrices precisely. It is guaranteed to count all possible paths for you. Are there any questions about this example before I explain the magic behind this method? Anything about the calculation? All right, so how does this work? Formula or method works. So let's look at the simplest case, paths of length 2. Then the prescription is I should multiply 2 copies of A. Well, before I do it, how would I do it by hand? Well, suppose these are by, I have labels, right? So I'm interested in paths of length 2 from V sub I to V sub j, where I and j are two indices. So if that length 2 means that I should use up 2 edges. So I need some intermediate vertex, right, before I arrive to V sub j. These paths just look like 2 edges, which are linked in the middle through some intermediate vertex. And this intermediate vertex, as far as we're concerned, can be any vertex, right, if there is a connection. So there are paths passing through V1. So such paths passing through V1. Then separately, I can calculate paths passing through V2. And separately calculate paths passing through V3 and so on. I should try, as an intermediate vertex, all vertices I've got. Right? There may be no connections, then there will be 0 paths at that time. And in general, multiple edges are allowed. So, for example, looking at the first situation, when the intermediate vertex is V1, I may have some m edges between V sub I and V1, and I can have m edges between V1 and V sub j, the final vertex. I'm drawing all of them. So if I am to count all paths of the type, I have to choose the first edge, which will go from V sub I to V1, and I have n choices. And I have to choose the second edge, which goes from V1 to V sub j. And there are m choices there. By the product rule, there are n times m different paths of this type. Well, if there are no edges between V sub I and V sub 1, then n is equal to 0. And of course I would have 0 paths, because I couldn't even then get to V1 if there are no edges connecting to V1. Right? Similarly, if there are no edges between V1 and V sub j, I would get a 0 as well, and then I can think that in that case m is equal to 0. So this formula works even if there are no edges at all, right? In that case, either n or m or both are equal to 0, then I get 0 paths of that type. Same thing I should do for each other intermediate vertex, right? I may have multiple edges in the same positions, and say here I have k and I have L, I should multiply my choices. So if I have k edges of the first type, L edges of the second, I should multiply my choices to count all paths for which the intermediate vertex is V2. And I should do it for all other intermediate vertices. Right? The last will be V sub n, assuming there are n vertices in my graph. So the last possible vertex I should try for the intermediate vertex is V sub n. So I put dots here, right? And put V1, so Vi, Vn, and Vj. And then again, I can have many choices here. So there are P choices here and Q choices there. The total number of different paths will be P times Q. And then, since the intermediate vertices, they're all distinct alternatives, to do the total count of all possible paths of length 2, I should add up those individual results. So the total number of paths should be n times m plus k times L plus dot dot dot, the same products of numbers, and P times Q. Well, so what are all these numbers, n, m, k, l, p, q? They actually all sit in the adjacency matrix. Because adjacency matrix tells you how many edges you have between two given vertices. So this is the same as for n, I should take ai1, right? That's my n, because ai1 counts the number of edges between vi and v1, okay? And multiply this by m, which in using the adjacency matrix is a1j, the number of paths between v1 and vj, plus ai2 times a2j. That's instead of k times l, the numbers I just chose at random there. That's what they are. Plus, for the paths going through vertex v3, I'll have ai3 times a3j, and so on, until I arrive to my final term, which I denoted as p times q, but in terms of the adjacency matrix, this is ain times a and j. And now you see that it's exactly the formula for the matrix multiplication, right? That's exactly a times a, the entry ij. And you see now that in the matrix multiplication we're doing, in terms of multiplying numbers, in terms of operations with numbers, we are multiplying some numbers and then adding them up. So that's in the definition. And that realizes for us the product and the sum rules of combinatorics. Right? We use the sum rule when we count different possibilities of the intermediate vertex, and we're using the product rule when we're choosing the possibilities for the first edge and the second edge. Right? So interestingly, the matrix multiplication, which is defined in this strange way, right, which is very laborious, actually implements the counting rules of combinatorics. This can be extended to, you can keep counting. You can add another intermediate vertex, and then you'll have, sums corresponding to another matrix multiplication that they will be ranging over the choice of the second intermediate vertex. And then you'll have more products, right, which correspond to choosing 3 different edges. So that all organizes itself rather neatly in matrix multiplication of several copies of the matrix A. Okay, I think that's a good point to stop.